Morning, everyone. So we're going to finish off our periodicities chapter in this lesson here. Yesterday's lesson, we introduced transition metals, some of the specific properties of transition metals. We looked at them being multivalent because the 4s and the 3D were really close in energy. We looked at them being able to form complexes, which we'll flesh out today, specifically with the most interesting property is that transition metals in solution actually show really vibrant colors. We talked about them having magnetic properties here. Yes, even when we talked about paramagnetism, diamagnetism, yes, even if I were, let's say, P2, P3, I would have unpaired electrons, I would be paramagnetic, therefore, but when I have d electrons, because I actually have 5 d rooms at a time, it gives us a lot more ability to have unpaired electrons, which is why we attribute it only to transition metals. And lastly, we also did catalysis. Basically, transition metals can be heterogeneous or homogeneous catalysts, do memorized reactions like Haber process and the contact process. It's fair game for them just to be like state this and the state the catalyst has involved. Right? So I want to just flesh out for you more so that second feature that we did. This is actually getting us into a field of chemistry called coordination chemistry. Coordination chemistry, or crystal field chemistry. And basically, this is the chemistry of ligands, and it's trying to surround the metal. So the example we used yesterday here, we'll do it again. Normally, when we have a covalent bond, so we have fluorine, we're going to do all these Lewis pictures in the next chapter. But what we find here is for fluorine, the reason why it's diatomic is each F atom only has an unpaired electron. This unpaired electron would make it a radical, it would make it very, very unstable. What would happen here is these two atoms would collide. It's the outer shell, the second shell in fluorine that collides with the second shell. It's the unpaired electrons that potentially can do the bonding. Again, we're going to say this one here is a single bond. A single bond is made out of 2 electrons. This, I would say, is a normal coordinate bond because you see that 1 electron from each partner. So the fluorine contributed 1, the fluorine contributed 1, and therefore we get a single bond. The type of bond that we're looking at for a coordinate bond or a dative bond between ligands here is we actually have a metal. We are going to emphasize the fact here we're talking about the metals in solution, so when they are charged. We're going to have a ligand. I'm just going to generalize them as L. Make sure you can define the word ligand. Let's just do that right here. So ligand, remember we were saying don't be too specific when you're talking about what type of thing it is. I just use the term species. It's a species that donates a lone pair of electrons. You can flesh it out a little bit more depending on what it's actually donating to. So in our case here, donates a lone pair of electrons. The emphasis here is the pair. It's both electrons to, in our context here, to stabilize the transition metal center. Right. So it's a species. It doesn't have to be neutral. It doesn't have to be charged, but it's a thing that has a lone pair of electrons. Now, lots of chemicals have lone pairs of electrons. Because of that electron-rich region, it can actually take a bite out of this metal center, and we can actually try to figure out how close this ligand gets to the metal to try to stabilize the metal. And we'll do that interaction in a little more detail. This is referred to as a coordinate bond. We always draw arrows from electrons to where they're headed. So even though, the metal is also attaching to the ligand, I don't go metal, arrow, ligand. So from the electron pair to the metal center, called a coordinate bond or a dative bond. And you see that the special case here is both electrons from one neighbor or from one partner. In our acid-base chemistry here, I mentioned this last lesson as well. We're going to call this one here a Lewis base. A Lewis base is an electron pair donor, whereas a Lewis acid is an electron pair acceptor. They really like asking you state the acid-base nature of this interaction, and that's what they mean. In the more broad base definition, a base is actually something that donates an electron pair, both electrons in the bond. Some other features for ligands that will come back in today's lesson. Most of our ligands have been monodentate. These ones here only take one bite. They make one coordinate bond. They may actually, like fluorine, have multiple lone pairs, but by the time it's making a bite on one side, it can't actually bite with the other ones. I should mention here, by the time the bond actually forms, this bond looks like any other covalent bond. I wouldn't know unless otherwise looking at it that it actually came from one partner. Monodentate, we're going to use the terminology, the coordination number. That's why it's coordination chemistry. coordination number is how many ligands end up surrounding the metal. Again, in IB, we're just going to be using octahedral as my splitting. A ligand is going to come in left and right. That's 2. A ligand comes in top and down, so top and bottom. So top down. And a ligand also comes in front and behind. That pretty much surrounds this metal from all 6 sides here. Our coordination number is 6. Strangely enough, our geometry for 6, we're going to call it an octahedral. You might say, well, I thought octahedral was 8. Why are we only doing 6? It turns out, while yes, you might only have 6 vertices, if you imagine, I'm not going to be able to draw this. If you imagine we have a square in the middle, and we have a pyramid on top, we actually have 4 sides on top. With the one on the bottom, it also makes 4 triangles on the bottom. We actually do have an 8-sided shape that has 6 corners, so that's why it's okay to call it octahedral. It only has 6 vertices. So, we also talked about our ligands being ordered in what's called the spectrochemical series. Not all ligands are equal strength. Spectrochemical series, it is on section 15. And basically we had a stronger ligand, one that's higher up on the list. Stronger, we can even use that terminology, stronger field ligand. Stronger field displaces weaker field ligand. But these ones here are more equilibrium reactions. You might find, oh, how come this one here is weaker and this one here is stronger, and how come the weaker one is still attached? It could be due to how many of that concentration of particular ligand is actually present there. We did see in section 16 the odd case of things that were bidentate or polydentate. I asked you to look at the structure of EDTA. There are ligands that can bite more than once, and those are typically called chelating ligands. So let me just leave that note there. We do have polydentate ligands. There are a couple. You don't need to memorize them. They're on the chart, but we refer to these guys here as chelating. They form a chelate ligand. So that's just some background to the terminology here. We're going to revisit some of this terminology as we look at the coolest property. In this case here, we're going to look at how come transition metal ions actually are colored in solution. This is one of the favorite questions, so make sure you know the answer to this one. So I want you to picture with me here. I know I can't demo it in front of you, but let's just say the question here is, explain why CuSO4, that's our copper sulfate that we use in a bunch of labs here, is blue in solution. Okay, so this is sort of hitting that very last feature of a transition metal. Didn't quite get to in yesterday's lesson, but this is definitely the most interesting one. Pretty much in our labs, when you dissolved, first thing, the powder itself was already a blue color. When you dissolved in water, it definitely showed that really nice blue hue, right? So the question here is, how come the copper sulfate is blue? What I want to emphasize here is we are talking about copper plus 2 as an ion. It's the ion that's colored. I know copper metal is like a bronzish, kind of brownish metal as well. I'm not talking about the metal itself's color. So when transition metals are put in solution, when they're in the charged form, I want to be able to explain why it's colored in general, and later on this lesson, what the color depends on. So let's step our way through here. We start off with copper sulfate. It's a hydrated form. It's blue. It's solid. We drop into water. Some of it managed to dissolve, right? It's soluble. We break out to become copper plus 2 and SO4 minus 2. That plus 2 here does, with a higher charge, make it a little bit less soluble, but it does overall break up. We've seen this one here end up as a blue solution. We're going to focus mainly on the transition metal. How do I know that here is if I have other solutions, let's say sodium sulfate, it's colorless. If I have lithium sulfate, it's colorless. So I know it's not because of the sulfate ion, but it's actually this transition metal ion, when it is in the charged form, that actually shows a blue color. This actually is really useful when we do our reaction kinetics in, next year. If I have a reaction that produces copper ions, the blue color will get more and more intense. Or if I have a reaction that destroys copper ion, the blue color will slowly disappear. How quickly that happens, I can measure the rate of reaction. The amount of blue will tell me how much is there. I actually have a really good hold on how many, to measure the reaction itself. Right? So here's how the analysis goes. So we have just dissociated. I have poor copper here, plus 2. Let's start off with the configuration as well. Careful copper is one of our exceptions. I'm just going to do simple configuration because I know the inner shells just come along for the ride. I'm going to have argon, 4s2. It would have been a 3d9. If you remember back in chapter 2, this was one of our exceptions. Well, we have a 4s. We just emphasized 4s and 3d are really close in energy, so not that hard to actually promote an electron up. We see that copper actually is just one short of having a full shell. So what's going to happen here is, as an exception, always, just natural copper, it's going to say, fine, I do need to pay a little bit to get that electron up here, but phew, I'm going to end up getting a fully filled D shell, and that full D shell ends up giving you stability. Full D shell stability. Sort of like your noble gases are stable, although we see for a lot of transition metals, they can be stable with any number of D electrons. So already as an exception, I have 4s1, 3d10. Remember, it's not just having D electrons that makes me a transition metal, it's the notion of my ions. When I become charged, do I have a partially filled D shell? Fortunately, by the time I become copper plus 2, I would remove the other 4s, that's now gone. I remove P, S, and the D in that order. And I remove that one electron, I take away that stability. It doesn't want that to happen, but no doubt, copper is now argon and 3d9. If you compare it to other transition metals, they're also going to be colored for this reason. They're going to have a different number of D electrons, but what we're going to really be hoping for here is partially filled. And guaranteed in that technical definition, the ion will, at least one ion will have to be partially filled. So here's what's going to happen. We have our transition metal. When our transition metal is just sitting in solution, when it's just sitting there, our energy level diagram here, our d orbitals are actually degenerate. Okay, so these are my 3d orbitals. We're all at exactly the same energy. So let's use that terminology here. All my orbitals are degenerate. All 5 orbitals are equally good to sit in. There's no one that's better than the other. So degenerate meaning equal energy. That's just plain old copper though. We know that this copper here is unstable with its positive charge. What's going to end up happening is this copper ends up getting surrounded by water. Right? I'm going to assume water is my ligand, or it could have been any ligand. So water is going to come in. I'm just going to put ligand. Right? You can assume that this is water, pointing its oxygen side. And basically the ligand is going to force its electrons onto the copper. We mentioned it's just trying to stabilize the copper. We do the coordination number 6, so 6 ligands end up surrounding this metal here. So the ligands, again, the water unfortunately here is a neutral molecule. It can't actually get rid of the charge. Even when by the time I form a complex, I would be Cu with 6 waters. I would still have an overall charge of plus 2. That gives rise to another question we can do later on. But basically what's happening, again, the hot potato example, it's not just going to be the copper ions itself that actually the copper ion itself that actually holds the hot potato by itself, being formed in a larger complex ion. The complex ion is made out of part transition metal and part ligand. It actually helps to share that transition metal's charge. Here, be careful, 2 things happen. Okay, so I want to just write this down in words for you so you have it. As ligands surround the metal to stabilize the positive charge, we have to remember that the copper itself already by itself had D9. So it wasn't like copper just had an empty D shell. Copper would do our Hund's rule. Copper already had this. Now, in terms of valence electrons, this losses S and P's. I know that. It's not valence anymore. But because I have D9, even though my ligands do want to come close to stabilize the positive, my ligands are going to actually experience repulsion. As they try to coordinate bond, as they try to share both electrons, they're going to interact negatively with the D electrons. We'll draw these orbitals in a second here. We're also going to get some repulsion. The ligand is trying to get close to the metal to stabilize, but as it gets too close, it's going to now start interacting with some of these D orbitals as well. The electrons on the ligand hate the electrons on the D orbital. There's going to be repulsion. So, as ligands surround the metal to stabilize positive charge, the electrons on ligand are repelled, so sort of a compromise here. I want to get close because I want to stabilize it, but I don't want to get too close because our electrons are actually head-to-head and repelling each other. Electrons or ligands are repelled by the D electrons. And in fact, what happens out of that compromise, we're going to study this based on the shapes here, it actually ends up pushing, because of that repulsion, it pushes all 5 to a higher energy. So because of the added energy to force the ligand's electrons onto the metal, in some sense it wants to get close to stabilize, but because it's running into a lot of the d electrons that are also negative, all 5 shells go up in energy. And in fact, we're going to look at the shapes of these d orbitals. We're going to find 3 of them are a little bit better off, 2 of them are not as good, right? So to explain not just it going up in energy, to explain how come the d orbital split, we actually have to look at the shapes of the d orbitals. Up to this point, we've been drawing the shape of the s orbital, shape of the p orbital, the shape of the d orbital. This all comes from the Schrodinger equation again. I'm just going to do this on the side here. 3 of the d orbitals, I'm going to call them dxy, dxz, dyz. 3 of the d orbitals look like butterflies. So let me just draw this here. See if you can color code it for yourself. When I say xy, the butterfly is actually sort of, there's 4 lobes, but that's 1 d orbital. So Pauli says this one at a maximum can only hold 2. They could both appear here. They can be 1 on this side, 1 on this side, but at a maximum it's only 2. So the butterfly shape, but along the x-y axis. You may have guessed it, like the p orbital is 90 degrees off. If I have the xz axis, butterfly shape, again that's 1 d orbital, but it's 90 degrees off. The yz orbital here is also 90 degrees off. That's the sort of cheating way of actually analyzing it, because I actually changed the axis on you. If I plot this on a 3D diagram, here's what I mean. So x, y, and z is in and out. The xy, I colored it black. So on the flat plane, on this flat structure, we have the butterfly. It's not actually flat. It actually is a lobe, but just for simplicity, I'm just going to draw it along that plane there. When I have the xz, I'm actually not looking at the in and out plane anymore. I'm looking at the up-down plane. So 90 degrees off. This one here is going to look very messy very soon. So this one here is going to be like up and down. So 90 degrees off from the original orbital. And dyz, to make matters worse here, dyz is actually looking at the plane that's in and out of the axes. Just like your p orbitals, they're just 90 degrees off. That just looks like a big mess. Okay. These 3, although they did get pushed higher in energy, they do experience some repulsion. They luck out a little bit. Because what's going to happen here is my metal is just sitting here at the center. The ligand can sort of squeeze its way in. The ligand has some negative density. They can sort of squeeze their way in, just sort of in between the lobes left behind by these butterflies. They're going to experience a little bit of repulsion, but not as much. So in that case there, they do go high up in energy. 3 of them are so degenerate. The question here is, what about these 2 up here? Why are those 2 worse off? Now, they're not worse off by too much, but it turns out when I solve the Schrodinger equation, when I do all that wave equation stuff, figure out what the orbitals are doing, the equations that tell me about the electrons here, I'm going to have one that's called d x squared minus y squared. You're already scared. The other one is called dz squared. These ones here are perfectly the same as d orbitals, but basically what's happening here is when I get the shapes of these, I actually end up getting a sort of funkier shape. The dx squared minus y squared here, it's very similar to the dx xy on the xy plane. It's also a butterfly shape, but the butterfly shape here is actually on the axes themselves. So it's like a butterfly. These 2 are 45 degrees off from each other. So on the xy plane, on one of these papers, we're going to have one plane that's actually, there's another butterfly there. One, the dz squared just looks crazy. So I have a d on a xyz axis. And this one here almost looks like one of those baby pacifiers. There's a donut in the middle. We have a 1 up, 1 down. Strange, it just comes out of the math from the Schrodinger equation. It used to be perfectly degenerate, perfectly equal energy, even though it has a totally different shape. But what we're noticing for those 2 is, unfortunately, these ones here, they have some density here along the axes. So what's going to happen is, when the ligands force their way on this, along the axes, we're going to actually experience a little bit more head-to-head attraction that I didn't experience when I could sort of work my way in between the lobes left over by the butterfly. So those 2 in particular end up higher energy. So you can say here the d orbital split because of this electron repulsion. And here's the kicker. How much do they split by? We'll call it delta E. That's an energy gap. It turns out the delta E gap is visible. Right? So let me just flesh out some of these details here. When we start doing Hund's rule, because of this splitting, it's split whenever there's ligands around. When we do Hund's rule, we're going to go single, 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 D3. my D4 used to fill up my fourth room, but because the fourth room is now higher energy, my D4 is actually going to be down here, D4, D5, D6. That would be a condition called low spin because all of them are actually on the bottom. As I do get to D7, sure, I need to occupy this one. I do my Hansdro and my D9. What you're going to be really watching for here is you want to have a space on this top. All right. If you don't have a space on the top here, what's upcoming next won't happen. It doesn't matter how many spaces. You can have all of them empty on the top. It doesn't matter. As long as you have at least one spot, which copper does, the rest of this will now happen. Because this energy gap here turns out in the visible region, what's going to happen here is always constantly white light from the environment is shining down on it. White light here has that whole Roy G Biv of colors. There's going to be one color that is perfectly the right energy, perfectly the size of this gap, that allows the electron to jump up the gap. So what's going to happen is white light comes in with all the colors, constructive interference makes it a white color, but one of the colors is actually going to get absorbed away. The color that is exactly the gap of this delta E. Because that color doesn't make it through, we're going to end up seeing the complementary color. So let me just write that down in words here. So that was the first point. We have that d orbital splitting. As white light passes the split d orbitals, electrons, the naming I'm going to do this is I'm going to call it internally promotes. Internal promotion is from the lower set. These are d orbitals, these are also d orbitals, but if the energy is exactly right, the electron can actually absorb this radiation just like we did in chapter 2. We used electricity in chapter 2 to do this, but it absorbs one particular color. That color no longer makes it through. Electrons internally promote, absorbing a specific color. That corresponds to delta E. And what ends up happening here is, this is where your data booklet, it's a little funny, it actually gives you a color wheel. I'm told you're supposed to learn this in elementary school, and I never did, so I don't know. So color wheel, we have a sort of Roy G Biv. At first, when we have white light, things are perfectly matched up. Things are perfectly constructively interfering. Red is matched up with blue, shows colorless. Orange and indigo, sorry, there should be a green as well. Orange and green, these are perfectly matched up. It's showing white color. But what's happening here is, because one of the colors is now being absorbed away, in this case here, I'm actually telling you it actually absorbs red. If I had a red laser pointer and I pointed it towards the copper sulfate solution, you'll find the red color light actually doesn't get absorbed. Because red has lost, the blue has lost its partner, we're going to end up seeing the blue color. So the reason why the solution looks blue isn't because it's absorbing blue. It's not sucking away the blue and then somehow showing off the blue. It's because it's sucking away the opposite. So you're just going to finish this off here and say, since I didn't know this until experimentally, so since red is absorbed, the complementary, the opposite side of the color wheel, the complementary blue is, I would use words like transmitted. That's the part of light that actually managed to get through, or you can say reflected. I would try to avoid the terminology of emission or emitted, because emitted usually implies, well, electrons following the give-off color. It is true that electron will eventually fall downwards, but there's enough other copper solutions to absorb more red color and then overall showing up blue. So that's why transition metal ions, especially when they're in complexes, they end up showing off these colors. Last couple notes here. We want to be able to distinguish here. They may not ask you what exact color it is, but they will ask you in general what the color depends on. And in this case here, so color, based on our analysis here, color is going to depend on delta E. Whatever you can do to change the size of this delta E, if you can change the size of how much is actually being split, that's going to change which color is actually absorbed, and that's going to change which color is my opposite. Right? Let's think about here, how come there was a delta E? It was because my 5d orbitals had a different shape. It was only when your metal was surrounded by a ligand. So anything I can do to this interaction, how the ligand forces its way on the metal, I can actually change the color. So what are some things I can change for the metal? Right. For the metal, I can consider different elements. Okay, so let's just have different protons. Let's go from scandium to titanium to vanadium. These all have different protons. Different protons would come along with different sizes, so different radii. Right? I know the trend was a lot less dramatic. Different sizes will mean the ligand will get different closeness to the metal center. It can be oxidation state. It can be those funny charges that we had from earlier. Let me give you some examples of this one here. Let's say I compare scandium plus 2 to iron plus 2 to copper plus 2, right? We're slowly picking up more protons in that order there. My radius is shrinking. The ligands would generally get a little bit closer. That splitting will be a little more dramatic. Oxidation state, maybe it is the same metal. Maybe it's iron 2 again. But what if I become iron 3? The more positive attraction, again, the more the ligand is going to want to force its way onto it. That's going to cause even more splitting. You will have splitting as long as ligands are around the metal. How about the ligand? Here's where we can rehash some of the terms from earlier here. Ligands are also differentiated by their strength, their stronger field. Okay, this is from what's called the spectrochemical series. Some ligands are just more electron rich than others. There's that ordering in section 15. The denticity. If I swap out a ligand that only bites once with a chelating ligand that bites twice or 3 times or 4 times, every time I bite, I'm going to get even closer to the metal center. That would also have some impact on the ligands repelling away the d electrons. Coordination number. We said the most common geometry was octahedral, like 6. But we're going to see examples later on. Well, what if it's 4? And what if it's sort of a tetrahedral? What if I'm not trying to come in sort of top down, up, left, right, front, back? What if I'm trying to come in along a tetrahedron? Or what if I'm trying to come in along a square planar? We'll do all these shapes more so in the next chapter. But in this chapter, at least, you just want to see, based on which angles I'm coming in, I may experience more or less repulsion. So make sure you can definitely explain why transition metal, again, it's the ions that are colored. There are 2 that are not colored. So they might say, explain why scandium plus 3 and Zn plus 2 are not colored in solution. And it really comes down to just the configuration. Scandium would have been argon, 4s2, 3d1. Having lost the 3 electrons for the stable charge, I lose 1, 2, 3. I might still get the splitting as earlier, right? As long as ligands surround it, it's going to split, but I have no d electrons at all. Even though this is in the size of the visible region here, I have no one willing to actually jump the gap. There's no d electrons. Zinc has the opposite problem here. Zinc would have been an argon, 4s2, 3d10. Upon losing the 2 electrons, that's why transition metals typically have plus 2 no problem. They just lose 2s electrons. Zinc, unfortunately, even when I do the Hund's rule, single, 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 pair, 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 that's diamagnetic. Single, single, pair, pair. I have all of it full. I don't have any room up here, so therefore no electrons can jump from inner room to upper room here. Because I can't absorb that colored wavelength, so therefore I'm not colored in solution. Which is why it's okay for, when we define transition metals, why were we so particular that their stable ion actually has a partial field shell anywhere from D1 to D9. It was for this property. Because I have a partially filled shell, again, any number of spaces up above, so electrons can internally promote. So, no room to internally promote. Well, this one here is no d electrons to promote. So they really like asking those questions, be it multiple choice or explaining why that's the case. The one last little spin off of this, especially with this complex chemistry, because we're actually forming complexes with transition metals and they're surrounded by ligands, I can end up getting some fancier charges. So let's talk about this in terms of oxidation number. Just as a question here. Let's do ionic compound K3 FeCN6, and let's do PT NH3 to CN2 and plus 2. Right? So they gave me just 2 random complexes here. What they're going to ask you to identify for me here is what's the charge on the complex, what's the charge on the ligand, and what's the charge on the transition metal. This is sort of like your ionic chemistry stuff, just sort of matching up charges, just gone crazy here. K, I know is an alkali, it's a +3. I needed 3 of them to counterbalance everything inside the square bracket is the complex. What charge does a complex have? Hopefully you're able to save to me -3. The ligands, if you look at table 15, spectrochemical series, the ligands will always have the same charge. Cyano, we're told, is going to be a -1, so that's going to be a -1. When iron gets surrounded by 6 things that are negative, it gives me an overall charge of -3. What charge is iron using? And the reason why this is an interesting question is because transition metals can be multivalent. We can actually figure out which charge it's actually trying to use. So in this case here, the transition metal should be 3. I'll draw you a picture of that. So this is my complex. That's what's in the square bracket. If iron uses its 3 and it's surrounded by 6 things, we do oxidation number per ligand or per atom. So in this case here, each of the ligands is -1, but there's 6 of them. 3 minus the 6 gives you a -3 overall. That's why I counterbalance it with 3. For this other one here, just to finish off, the complex itself, it's already the square bracket. I didn't give you any compound. I already told you it's +2. This one here, I actually have 2 different ligands. Cyano is actually the stronger ligand, but again, depending on the proportions, I might still have an ammonia ligand. In tables 15, ammonia is a neutral ligand, cyano is a -1 ligand. Hopefully you're able to tell from me here. Okay, I just did the ligands up there. But at least the transition metals, whatever charge platinum has, the ammonia doesn't do anything. Adding 2 negatives leaves me with a +2. Hopefully you can say to me the transition metal is a +4 charge. For the ligands, you can just do separately. Right? So that does finish us off for the periodicity unit here. I'll give you the study guide questions so you can just be practicing. If you have any questions, just let us know. Thanks.